The name of this video is Circuit Force Bulk. In fact, we are going to generalize the result in the previous video, which was the force acting on circuits which carry a steady current I in presence of an external magnetostatic field B naught. In this case, instead of considering filiform or quasi-filiform wires, we are going to consider bulk conductors. So, for example, we can consider a part of a bulk conductor which has finite dimensions, so nothing is small compared to anything. So basically we have, for example, here some cross-section like that. If we cut a big wire which is really bulk, and it goes, let's say, like this. This is the cross-section of our wire, and let's say that in this case, the procedure we need to do in presence of bulk conductor, so this is a bulk conductor characterized by a volume, by a region, volumetric region, capital omega in the three-dimensional Euclidean space. So in this case, what is the procedure we need to follow always when considering currents in presence of bulk conductors? We have seen this in 242 already, where what has to be done in this specific case is that we need to split this object in an infinite set of filiform flux tubes, of filiform infinitesimal flux tubes. So let's show one of these flux tubes. So for example, here we can consider a flux tube with cross-sectional area, obviously dA. This is my cross-sectional area here, which is, as always, dA. And now we consider one of such tubes, which continues throughout the entire conductor. I just sketched part of it in this fashion. The central axis of this filiform flux tube, we call it, as always, gamma. Okay, so this is a filiform, because we assume the cross-section to be dA. If it was delta, it would be quasi-filiform, a filiform flux tube. So we need to remember the definition of flux tube, which we have seen extensively in Phys 242. So in the case of charges, whenever we have a conductor, a bulk conductors, we need to split it into sub-pieces which have a charge dq. And in this case, we want to split it into spaghetti, remember 242, that is filiform flux tubes, which means infinitesimal flux tubes. An infinite set of them eventually allows us to rebuild the entire conductor. We've seen this again in 242, and I called them a spaghetti back then, okay? So you can have many of these spaghettis. All right, so what is the current? Suppose that there is a current density vector J in this region, a capital omega space, okay? What is the current intensity associated with one of these flux tube? Well, let's call it dI. This is the current intensity associated with one of these filiform flux tubes. dI, because it's infinitesimal, because it's a filiform flux tube. Okay, what is the definition of a filiform flux tube? So, if I want to find my current dI, obviously, this is nothing but the flux, definition of flux tube, the flux of J dot n dA. What is n with respect to dA? Well, if I pick a point, let's say right there, the tangent unit vector, we call it T, tangent unit vector, which is exactly the same as the normal unit vector at this area here. So they are exactly the same quantity definition of filiform flux tube. So T is also the direction of J. So this we can rewrite it as J magnitude times its direction, which clearly is that of the flux tube of gamma, that is T. This has to be dotted with n, but n is nothing but T again. We have done this already in 242 times dA. So finally, what we find is that dI is nothing but J magnitude times dA. Okay, definition of flux tube. Great. So with this in mind, now the next question which I have is, what is the force dF associated with this filiform flux tube? And then by integration, we can find the force on the entire bulk conductor. So the force dF, we need to use the result from the previous video, which was for a filiform wire. Now, one of these flux tubes, and again, I need an infinite set of them to rebuild the entire bulk conductor. For one of them is going to be the current, which, remember, it was I. Let's call it dI in this case, more properly, is the current associated with one filiform flux tube, times dl, t, vector b naught, if this conductor was in presence of an external magnetostatic field B naught, precisely as we have done in the previous video, with these lines, like this, let's say generated by an external source. All right, of course we consider this rigid. So under these conditions, we can rewrite this force as dI, which is nothing but J dA, from this definition down here. This is my dI here. It's nothing but J dA. dA times dL, but what is dA times dL? We already know that this is the volume, the infinitesimal volume delta V associated with the filiform flux tube. So we have J dA, which is dI dL, dL T vector B naught. So this dA dL, we recall it, we define it as dV. Therefore, we obtain J direction T crossed with B naught times dV, okay, which is nothing but the A dL. So let me just write it here. This quantity is nothing but dV, which is what we put here. What is JT? JT is nothing but J vector. And therefore, this current, this force, dF, we can rewrite it as J vector, the vector density, crossed with B naught dV. Okay? So in general, if we assume that this object is not rigid, so let me generalize it in this video a little bit. In the previous video, I just said that typically we only consider rigid objects, that is, for example, rigid wires, and rigid means they cannot be deformed. What is the definition, let me give it here, of a flexible conductor in general? This can be a wire or a conductor in general. So here I just call it conductor because we are in the bulk case, but this applies also to wires, if you go back to the previous video. A flexible conductor wire means it can be deformed. Can be deformed. In this case, one part of the conductor or wire can interact with another part because they're flexible, and these interactions effectively behave as they make it effectively flexible, and this interaction force you to use, instead of only the external field, also the internal field. So in that case, if the wire is flexible, this is for rigid, as we've done before. If instead I generalize it further to a flexible wire, which again we don't typically do, but I want now, since I'm generalizing this law to as general as possible, I want to make it flexible on top of it. Again, in this course, we're never going to consider flexible. In that case, anyway, the total field is the one which actually we need to consider, which is B naught plus linearly superimposed with the field B1 generated by J, which is the internal current density here. Okay, so for flexible, you need to consider both. Remember that a single rigid is like a single particle which can only be translated or rotated in space. Flexible, it allows interactions between subparts of the system, and therefore we need to consider the effect of the external field, of the internal field, of the external and internal field, of both, okay? So where the addition is really the internal field, okay? This one is my internal field, I remind you. That is generated by J, okay? We've seen this in the previous video. All right, so now we are generalizing as much as possible. So under these conditions, the force dF in presence of flexible conductors or wires, which is a subcase of that, is going to be the J vector total B field dV. So if this is the local form, if we integrate it, we find that F, the total force on the entire bulk conductor, is the volume integral on the entire region, capital omega, of J in dV of J vector B. And of course, I ask you, if you want, you can try to rederive, so you can do this in Piazza, attempt to rederive from this equation the previous one for a filiform wire, which again is a subcase. And if you do rigid, of course, you need to forget about the presence of B1. So what we've done in the previous video is a subcase of this case we are looking at here. In particular, this quantity here, J vector B, people call it small f. Small f is the force per unit volume, and so it's nothing but dF from this definition here, renormalized over dV. And so if you want, you could rewrite this as the integral of this force density vector B if you want, but it's not necessary to do so. Okay, it's just a definition. J vector B is the force density. Okay, all right. And so this one is the, let me highlight this equation, which is the fundamental one. This is the most general equation you can have for the force on an infinitesimal element of volume dV of a conductor, flexible, which carries a steady current. In this case, let's say steady, but can be not even steady, J. But in this case, let's consider steady. We eventually could generalize it also to non-steady currents. Cross with B, which is the linear superposition of the external field and the internal field generated by J, dV. I can integrate over the volume, and as a subcase, I can reobtain the results of the previous video. So to summarize here, we generalize as much as possible the concept of force on a circuit to make it bulk. So a bulk circuit, so it becomes basically a conductor. Okay, so it's you can still call it a circuit, but you need to specify the fact that it's bulk because there's finite dimensions everywhere in all possible directions in any coordinate system. And so the trick, as always, is to split this conductor in an infinite set of spaghetti, which are my filiform flux tubes. Once you understand that, then you use the definition of filiform flux tube for steady currents, which is what we are considering here, and we generalize the force we found in the previous video to this very general case, which applies to is as general as possible, in particular also to flexible conductors. But again, in this course, we will never consider really flexible conductors, and at most we'll consider also filiform conductors, as in the example we're about to do. That's it.